This production is brought to you by the University of Edinburgh.
Okay, so we're going to go back to the handouts and I'll give you a recap of where we got to on Friday. We did complex Fourier series and we did an example of analysing this rectangular pulse, and we found that if we plotted basically the Fourier coefficients as a function of the index, then we ended up with this sync pulse. So the sync pulse you really want to get your head around, make sure that you can analyse the sync pulse multiple times. I did have a question, why were we looking specifically at the zero crossings? Well, whenever you're trying to plot a complicated signal, it's always good to look for points that have some meaningful value, and you basically then draw curves in between them. So the reason that we were looking for these crossings here was just because then it made it easy to draw the sinusoid, well, the sync function through it. We then argued that if we replaced the Fourier index n, which was an integer, with actually a continuous frequency omega, I could interpret this as basically being a spectrum. So I've got frequencies at, in this case because the period of a waveform was 1, I've got frequencies at 2 pi, 4 pi, 6 pi, 8 pi and so on. And the spectral components that exist are only at those integer multiples of 2 pi. So there is, for example, so 2 pi is, what, about 6.3 or something. So there is no frequency present at 1 radian per second or 1.5 radian per second. There's a frequency present at 0 at DC, and we know that because if you were to draw the average value through that waveform, it's obviously got a non-zero DC offset. So we've got essentially a 0 frequency, and then nothing until 2 pi and 6 pi and so forth. So that's what we did, so get used to that. Now, complex Fourier coefficients are usually complex. This was a well-chosen example which didn't end up with complex coefficients. In general, they will be. So we should really be plotting complex numbers. So the most effective way of doing that is to plot these Fourier coefficients as a function of frequency, as the magnitude of a complex number and the phase of the complex number. So what we did on Friday was to draw these two diagrams here. Okay, so on the top was the magnitude, so that was fairly easy. The phase was a little bit more awkward because we had to sort of think about what's the phase of a negative real number. So I argued that was plus or minus pi, or plus or minus 180 degrees. And we have a convention that for a positive frequency, the phase of a negative number, a negative real number, is minus 180 degrees or minus pi. And we also saw that the phase, i.e. the angle of a complex number, is basically it's asymmetric. It's odd symmetric. So you can see that's a symmetric waveform, but it's odd symmetric. So that's where we got to last time. Okay. Some of the properties of the Fourier coefficients were then listed on slide 12. So really, I think maybe you can go and have a read of that. But remember, on an earlier slide, I came up with an equivalence between the complex Fourier coefficient x of n and the trigonometric Fourier coefficients a(n) and bn. And it was possible to sort of show that, in fact, with a couple of sort of subtle redefinitions, which are really just notation, it was possible to write the complex Fourier coefficient for all values of n as just this expression here. So if you've done the trigonometric Fourier series and you found the a(n) and bn, you could recombine those using this expression here to get the complex Fourier series. And equally, if you've got the complex Fourier coefficients to start off with, so if I've got the x of n's, then I could get the a(n) and bn quite simply by taking the real and the imaginary part of x of n. Yeah, so I could rearrange that formula. So I could write an minus jbn is 2 times x of n, and we know that an and bn are real. So in fact, I could do something sort of slightly more subtle, and I could take complex conjugates of both sides, which changes that minus j to a plus j. So I've got an plus jbn is 2 times the conjugate of a Fourier of a complex Fourier coefficient. So in principle, if I wanted to find an, I just take the real part of 2 times x of n conjugate. And in fact, the real part of x of n conjugate is just the real part of x of n. And similarly, bn is 2 times the imaginary part of x of n conjugate. Or in fact, that will probably just turn out to be minus 2 times the imaginary part of x of n. So you could do that. So there is one question in the tutorial sheet that gets you to work out the relationship between the trig and the complex Fourier series. Now, one thing I would say is that depending on how you do some of these manipulations, you can often come out with equivalent expressions that are in fact correct, but look slightly different to the final answer. So I think if you have a look in the tutorial sheets, if you get a slightly different answer to the one in the tutorial sheet, do check with me, because it might possibly be correct. Okay? But you might want to try and manipulate it to see if you can get the same answer. So it's not necessarily that you've made a mistake, although to be fair, you've probably made a mistake. But if you've really sort of gone through it like 3 or 4 times and you still just can't get the answer in the tutorial sheet, it might just be that there's a simple manipulation that to get it in the right way. Okay, so we've got the other relationships here, which I've already been through, which they basically sort of denote what I've already put on a previous slide. So we're going to have a quick physical interpretation of the complex Fourier coefficients, because you might sort of think, how do they relate to the real world? So if we go on to slide 13, I've got a whole bucket load of text there. Let's look at the green box first of all. So in the green box, I'm going to make a relationship between the trigonometric Fourier coefficients and an actual sort of real signal. So if I took the nth harmonic, so you take the trigonometric Fourier series and you just take one of the harmonics, and that harmonic is at frequency n omega naught. So the nth harmonic consists of a cosine component with amplitude an and a sine component with amplitude bn. And x of n of t is your nth harmonic. Now the question is, can I just simply rewrite that in terms of the complex Fourier coefficient, the magnitude of x of n? So how can I do that? And the answer is you can. So you can go from this green box to the red box, and I'll explain how you do that in a moment. But basically the nth harmonic can also be written as 2 times the magnitude of the complex Fourier coefficient, now times the cosine wave of frequency n omega naught, plus the phase, or the angle of a complex Fourier coefficient times the phase of x of n. So you work out your complex Fourier coefficient x of n, take the magnitude, take the phase, and you recombine it into that equation in the red box. So the physical interpretation is exactly that formula there. Right, so how do we get between those two? Virtually all the time with these manipulations, it's always through application of a trig identity. So you will get a data sheet in the exam which has trig identity. So if you ever need to do a manipulation, you don't need to remember them. But basically, I'm going to rewrite the expression in this green box using this identity here, which says, look, if I've got cos of a plus b, then cos of a plus b becomes cos a cos b minus sine a sine b. And similarly, cos a minus b becomes cos a cos b plus sine a sine b. And if I multiply both sides by r, then I've got that expression there. Okay, so what I'm going to do is to apply this formula there. So I'm going to apply the trigonometric identity to the nth harmonic of a trigonometric Fourier series and just manipulate it. So if you compared those and you set beta equal to n omega naught t, that's a simple one, and then you compare the other terms. So r cos a, or r cos alpha, that's your a of n. So you've got a of n is r cos alpha, and b of n is minus r sine alpha. So just matching up those two expressions. Anyway, so then the question is, how do we get the value of r? Anyone got any suggestions how we find? So what I'm trying to do is to find the values of r and alpha, because I've defined what beta is. So I'm trying to match these expressions. So if given I've got the values of an and bn, how can you find the value of r? So you'll square these two. So if I take an squared plus bn squared, that equals r squared cos squared alpha plus r squared sine squared alpha. And cos squared alpha plus sine squared alpha is just 1. So that just equals r squared. So in fact, the magnitude here, r, is a square root of an squared plus bn squared. No, because I tried to be probably a little bit too clever with writing too much stuff there, but you see where that plus or minus is. Just treat it as a plus, and then that becomes a minus. So minus over a plus means you've swapped it the other way around. So the only question is, what's an squared plus bn squared? Well, we already on the previous slide had a relationship that 2 times x of n is an minus jbn. So now, applying your complex numbers, if I took the magnitude of both sides, then 2 times the magnitude of x of n is indeed an squared plus bn squared, because it's the real part squared plus the imaginary part squared square rooted. So in fact, r is equal to 2 times the magnitude of xn when I plug that back in. So that works. So that's got our first part of the identity. And so then the question is, what's the phase alpha? Well, I just go back to these expressions here, and if I divided both of those, then if I divided bn by an, that's equal to minus sine alpha over cos alpha, which is minus tan alpha. So I could take inverse tans of both sides, and I'll get this with a minus sign in front. Remember, what I was really trying to do was to derive pretty much what was in the red box at the top of that page. Okay, that's how you get from that line to that line. So there is a physical interpretation there. There also seems to be a problem with is it? I know what happened last year. What happened was I had exactly the same slide, but without those two identities, because I thought it took too long to write those out. So I typed them in after the lecture, but obviously didn't check it, and it's just made things worse.
This production is copyright the University of Edinburgh.